My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 380. In this lecture, we will try to understand train and runtime complexity of support vector missions. So, we can train support vector mission using your standard stochastic gradient descent algorithm. There are specialized algorithms which solve support vector mission optimization problems, dual problems especially. There is one such algorithm called sequential minimal optimization. It is very popular algorithm, often referred to as SMO. If you just Google search for SMO SVM, you will get an explanation of this algorithm. We are not going to deep into because we never end up with implementing SMO. We don't have to implement. There is a very popular library called libsvm, which is one of the best open source libraries for training support vector missions. But scikit-learn implementation is not as good as libsvm. libsvm has only one algorithm, which is support vector mission, nothing else. It does a very good job of optimizing the code. It uses SMO internally. People came up with special purpose optimization algorithm just to solve support vector missions. The best library for it is libsvm, but we will continue to use scikit-learn, of course. Those of you want to explore libsvm, please Google search for it. There is a lot of documentation available for libsvm. Training time complexity of SVM is roughly order of n square for kernel SVMs. There is a nice optimized algorithm which came around 2007, more optimized algorithm that has time complexity of order n d square if d is less than n. Here condition is, what is the condition? If d is less than n. It is linear in n. What is this? Linear in n. I can say it is linear in n, but quadratic in d, isn't it? Yes. Order of n square basically means if you have large data, if n is large, millions of points, then order of n square is very large. If your n is large, then order of n square will be very large. Hence, typically most practitioners do not use support vector missions when n is large. N is large means you can think about internet applications, because in internet applications you have millions and millions of data points. When n is large, then order of n square becomes very large. Typically, support vector missions are not used when your dataset size is large. This is slowly changing because there are more optimized variations of support vector missions, just like order of n d square if d is less than n. There are internet applications where people are used support vector missions. It's not that you cannot use it, but you have to be careful. The time it takes to train them is significantly more. Now let's look at the runtime complexity. Runtime means what? What is the formula for what does it mean for given xq? Let me say like this: for given xq, this is given query point. For given xq, let me take like this. Just let me change the color. Yes. For given xq, how do I determine yq? Isn't it? What is f of xq? F of xq is sigma I equal to 1 to n alpha yi k into x, k of xi comma yq plus b, isn't it? Here, if you recall, alpha equal to 0 for non-support vectors. That means only for support vector this value matters, isn't it? This f of xq matters, isn't it? Why? Because for non-support vectors, alpha I equal 0. Runtime complexity, given xq, we have to find yq. Given query point, find its class label. Yq means what? Its class label. Depends on the number of support vectors. Let me say number of support vectors equal to k, isn't it? Let's assume number of support vectors equal to k. Runtime is roughly equal to, if number of support vectors is equal to k, what is runtime complexity? Roughly equal to order of kd. What is my d? D is dimensionality of the data. D is dimensionality of the data. Dimensionality of the data, isn't it? If the number of support vectors are small, then your runtime complexity will be small. The number of support vectors can be anything from 1 to n, isn't it? Number of support vectors, if number of support vectors are small, I can say if number of support vectors are small, then your runtime complexity will be small. But the number of support vectors can be anything between 1 and n, 1 less than or equal to k less than or equal to n. It could be very small, it could be very large. In the soft margin SVM, formulation, there is no way to control number of support vectors. If you train your support vector machine, let's assume you are doing RBF support vector missions, you have hyperparameters C and sigma, isn't it? In the case of RBF support vector missions, RBF soft support vector missions, you have parameters C and sigma, and let's say n equal to, let me assume n equal to 100,000, let it 100,000 points. Suppose you got number of support vectors k equal to, let it be 1000, isn't it? For optimal C and sigma star, optimal C means C star, optimal sigma means sigma star, because these are your hyperparameters, then your runtime complexity will be order of kd, isn't it? What is your runtime complexity? It's the order of kd. Just go through this particular lecture. If you have any difficulty, please keep a comment. Thank you very much.